This video is part of the MCAT Chemistry video course. Subscribe if you'd like notifications about the release of future MCAT videos, and please visit ancientbrainstutoring.com for questions about one-on-one virtual MCAT tutoring. In this video, we're going to talk about electrons and photons, and that's mainly going to be about how they interact, and then we will finish by talking about the photoelectric effect. First, we need to talk about what photons are. And photons are basically packets of light, and light also has wave-like properties. And all waves have a frequency and a wavelength, and then the frequency and the wavelength can be multiplied together in this equation up here to get the speed of the wave. And for light, the speed of the wave is 3 times 10 to the 8, and that equals the variable c. So c is only representative of the speed of light waves, where it's not representative of the speed of any waves. That would just be v for a wave that's not light, and we'll talk more about waves in one of the physics videos. But for now, we just need to briefly talk about waves to get a better understanding of light waves. So you want to memorize this equation very well, the c equals wavelength times frequency, and just be able to rearrange it and solve for frequency by dividing c by the wavelength. And all this is really important because we have this other equation here on the right, and what this gives us is how to calculate the energy of a photon by using the frequency of that photon. And it's a really straightforward equation. It's just the energy equals the frequency of the photon times h, and h is this Planck's constant. And Planck's constant is the number we have there, but I would only memorize 6.6 times 10 to the negative 34. You don't need to memorize the 26 because of how much rounding you can do on the test. But anytime that you see the frequency of a wave given, or if you even see the wavelength of a wave given, and then they're talking about the energy of the photons, this equation needs to be the first thing that you're thinking about, and then just be looking for how to find the frequency if you're given the wavelength, or just plugging in the frequency into that equation for the energy. And this is a super common equation that might be one of the most important on the whole test. And this ties into electrons because of the way electrons gain and lose energy. And we'll talk more about electrons and their energy levels in a second. But first, we just need to get this concept down where if an electron loses energy, it emits a photon. And so light, and this may be not visible light, but some sort of photon will be emitted or ejected from an electron anytime that it loses energy. And then if an electron absorbs a photon, it's going to gain energy. So just kind of be familiar with these ideas that when an electron loses energy, it emits a photon, and when it gains energy, it absorbs a photon. Now we'll talk about electron energy. And electrons occupy what's called energy levels. And we'll go over more of this in electron orbitals. But for now, just think of energy levels as spheres that surround the nucleus of an atom. And the larger the energy level, the further away you're getting from that nucleus. And what's really unique is that an electron cannot exist between two energy levels. So an electron has to occupy one of these energy levels. And energy levels are separated by energy. So if we look at our image on the left, we have our energy levels labeled 1, 2, and 3. So the difference between level 1 and level 2 we could describe as delta E. And this becomes really important when we talk about electrons gaining or losing energy. So again, if we look on the image on the left, we have an electron that's falling from energy level 2 to energy level 1. And remember, energy level 2 and 1 are separated by delta E. And when that electron falls, it's going to lose a photon, just like what we talked about a minute ago. And that photon is going to have an energy that's equal to delta E. So the electron lost an energy equal to delta E. That energy gets emitted as a photon, and so the photon's energy must also be equal to delta E. And so we end up with delta E, so the difference between those two energy levels equals the energy of the photon, which is equal to H times F. So if you were to have a way to measure the frequency of a light that's being emitted from an atom, then you could use that frequency to calculate the difference in energy levels. And this is where you get things like the hydrogen emission spectra, where you have atoms of hydrogen that are emitting certain colors of light, and we can use the wavelength of those colors to find the frequency of the light, and then use the frequency to calculate the energy of the photon, and then that energy of the photon is equal to the energy difference of the levels that the electrons are dropping in those hydrogen atoms. And on the right side, we have basically the opposite happening, where a photon is being absorbed by an electron, and the electron is gaining energy. So notice how that electron is going from level 1 to level 2. So once again, we have delta E, which is the difference between 1 and 2, is equal to HF of the photon that got absorbed. And it doesn't have to just be level 1 to level 2. we could have an electron go from level 1 all the way up to level 3, or from level 2 to level 3, just depending on what electron gets hit by the photon and what energy of photon we have. And it's really important to understand how this will affect visible light. So sometimes atoms will have energy differences that can absorb photons in the visible spectrum. So if you shine white light, and white light has all the wavelengths of the visible spectrum, if you shine white light at a atom or a substance that can absorb some of those wavelengths that are in the visible spectrum, it'll absorb some of the colors of the white light. And then those types of compounds are going to show up as the complementary color. So for example, if you had a substance that absorbed yellow wavelengths, so the wavelengths that would correspond to yellow light, then that substance is going to show up as the complementary color, which is violet. So just be on the lookout for questions about color on the MCAT, and you want to be thinking about photons and electrons absorbing or emitting those wavelengths of light. The last thing we'll look at is the photoelectric effect. And the photoelectric effect is when a photon strikes an electron and it hits it with enough energy that the electron gets completely ejected off of the atom. So the atom becomes ionized because it lost an electron. And again, this only happens if a photon has enough energy to do this. And the minimum amount of energy required to do this is called the work function. So the work function is a measurement of energy, and if a photon has more energy than the work function and it strikes an electron, then that electron will get ejected from the atom. And then if that photon had more energy than the work function, then the excess energy will go into the kinetic energy of the electron. And that is where we get this first equation right here. So the kinetic energy of the electron, which would just be the speed of the electron, equals the energy of the photon that struck it minus the work function. And sometimes there are questions that require you to think like that, and just make sure you're totally good on that. The more energy the photon has, the faster the ejected electron will be moving. And applying that to what we just went over, understand that as the frequency of the photon goes up, then the energy of that photon would also go up. And I would really emphasize to yourself that the frequency is what is correlated to a photon's energy. A lot of times they will throw out words like amplitude or intensity and try to trip you up and get you to think that a photon's energy will increase if one of those goes up. We'll go over those topics more in the physics section, but just make sure you don't get it messed up and always keep it clear to yourself that frequency is what is correlated to a single photon's energy.